Today we're going to learn about lenses and why our vision maybe needs a lens in order to correct it to make it a little bit better. First thing you have to learn a little bit about the eye. We have a lens that covers the top of our eye, which the whole goal of the lens is to bend light so that it immediately, as light hits the eye, the goal is to bend into a nice point back here on the retina. If the light bends to one crisp point, you get nice clear vision. If instead it spreads it out over the back of the retina and not just hitting in one spot, that's when you have blurry vision and you can't see quite as well. In the retina, we have a couple of things. We have the rods. Those react to black and white and in dim light, so that's what helps us see when in black and white and when there's not very much light. Then there's the cones. Those are the bright light and color vision. And then the lens is, as I said, it's there to bend the light so it hits right at the retina. When the light comes in, hits the retina, it causes the rods and cones to start to vibrate. Those vibrations send signal to your brain, and that in turn turns it into a picture of what you see. Lenses are very often used to correct your eyesight. There's two common ways to express your eyesight. The first one, we use an eye chart. Let's say you go in and you get your eyes tested using an eye chart. If yours 20/20 is what they consider to be perfect vision, so what you can see at 20 feet, everybody else can see at 20 feet. But let's say your vision is 20/200. That means what perfect vision people see at 200 feet, you need to be 20 feet away. Okay? At the worst, my vision was 20/750, so what perfect vision people can see 750 feet away, I have to be 20 feet, so I have to be much, much closer away from it. Sometimes you get a prescription in a decimal form. All that means is you just ignore the decimal place. Think of this as 325, so what perfect vision people see at 325 feet, you need to be 20 feet away. All right, we just got done with a unit on mirrors, and we learned that mirrors reflect light, which means when the light hits it, it bounces off and goes in a different direction. Instead, we are now going to be looking at lenses, and lenses are going to refract light, and refract, or refraction, is the bending of light. So when light hits a lens, the lens's job is to bend it. The shape of the lens and how much thickness it has is what's going to determine how much it bends it. The other thing about lenses is they're transparent. So if you look at an example of a lens here, they're transparent. You can see through them. So technically, light can go through both directions. They have a focal point on both sides of the lens, but we're only going to send light through one direction, so we'll always, just like with mirrors, we'll always put our starting object over on the left and send our light through to the right side. All right, so we're going to look at the two types of vision correctness that we deal with, and that is farsighted and nearsightedness. So we're going to start with farsightedness. If you are farsighted, it means you can see far but not near. So this is when you need reading glasses, something to help you see things that are up close. What is happening when you are farsighted is when the light hits the lens, it bends it, but not enough. So remember, we want it to hit at a nice crisp point on the retina. When it hits the lens of your eye, because of the shape of the eye, the shape of your lens, many different factors, the lens does not bend it enough. So instead of hitting in a nice spot here, it would hit in a nice spot there. The light converges too late. Okay, and what that does is it spreads out all the light rays throughout the retina, which means it's going to be blurry. So in order to fix farsightedness, we need a lens that makes light rays come together sooner. It needs to meet sooner in the eye. Converging lenses are what we use. To converge means to come together. So a converging lens means it makes the light rays travel through them, converge, or come together sooner. You will not be able to see the first one, but in class you will, but on the video it didn't work, I tried it. When you are far away from something in a converging lens, it will be upside down or inverted. Right? Then as you pull it towards you, all of a sudden you're going to get to a point where it gets super blurry. You have found the focal point. And then if you switch it around so that you get really, really close to the object, it is going to make it larger and upright. Hopefully these things look familiar. This is exactly what happened with your concave mirrors. Far away, something was upside down, then you pull it closer until it gets blurry, and then you pull it even closer to it and it makes it bigger and upright. I missed this part. Converging lenses are the ones that are thicker in the middle. So I'm going to bring it closer to the camera just for a second. This is a converging lens. It is one that is thicker in the middle. So the edges are thinner and then it gets thick in the middle. And then you can kind of see, oh, that worked for a second there. It was upside down. And then as you get closer to something, I forgot my paper. You can see how when you get closer, it magnifies it. You get to a point where right now I'm at the focal point and it's blurry. And then if I get it far away, it doesn't work well on the camera, but it's upside down. All right, we are now going to draw the diagrams to go with lenses. So just like mirrors, we're going to draw two light rays. We are always going to put the starting object over here on the left side. I will have the principal axis, so I'll have a dashed line for you. That's the midpoint up and down. And then I will put the lens in the middle. If it's converging, the arrows are like this to show that it's getting thicker in the middle. We will measure out a focal point. I measure them on both sides. You technically are only going to use one because when light hits a converging lens, it makes a bend through the lens and come together sooner. All right, so pick your first color. I'm going to go in red. The first line always does just like it did with mirrors. You're going to draw a straight line until you hit the surface of the lens. And then from there, the light ray goes through. But when it goes through, it makes a bend. So it's either going to bend this way or this way. For a converging lens, to converge means it's going to send the light ray through the focal point on the other side. So it's going to go through the focal point on the other side. It makes light rays bend and meet at the focal point on the opposite side. All right, so first line, straight until you hit the surface of the lens, and then through the focal point on the other side. From here, the second light ray, doesn't matter which type of lens you have, the second light ray, find the midpoint, the dashed line and the lens, right there is going to be the middle. You are going to send a line through the very middle of the diagram at the dashed line, the principal axis, where it hits the lens. And if you notice, they are going to meet and eventually come together way over here. All right, so as I look, I have an intersection point over here on the right side. It is below the dashed line. This is midpoint. If it's below, it is an inverted image. And this is going to be what we classify as, a real image. Light should go through. It should meet on the other side. A real image is going to be when it shows up on the right side. All right, then when we moved an object really close to it, it flipped it upright and it made it larger. This is how a microscope and reading glasses work. Okay, so I'm going to go back to my first color. For this one, we are going to have to extend our lines backward. All right, so we're going to start same as before. We're going to draw a straight line until we hit the surface of the lens, and then it's going to bend through the focal point on the other side. We are going to extend that line backwards behind the lens as well. Okay, second light ray always does the same thing. It starts here and goes through the midpoint, so where the dashed principal axis meets the lens, it will go through there. The light ray goes like this. I am going to extend my line backwards All right, notice these are never gonna meet. We had to extend our lines backwards, and they will now intersect back here. And what I have is what we see in the lens is going to be bigger than the starting object. Microscopes and reading glasses make things bigger. This is going to be upright. It is above, the intersection point's above the midpoint, so that is upright. And this is what we're going to call a virtual image. If it shows up on the left side of the lens, it's going to be a virtual image. We're not going to be able to project anything at that point. And then finally, we also, when we got to the focal point or the focus, this is where everything was blurry and there was no image. And it's blurry. Once again, there's a reason for this. It's because the light rays aren't going to meet. Okay, so we go back to first line straight until we hit the surface of the lens, and then we're going to bend it through the focal point. I'm going to extend it on both sides of the lens. It isn't going to matter. So I'm going to go through the focal point both ways. Then my second light ray always goes through where the principal axis meets the lens, that middle point right there. I'm going to extend it in both directions, and what you're going to see is you have two parallel lines. They never meet. If they don't meet, they can't intersect, the light rays can't come together, and they can't give you a clear image. So we have no image, and it gets really blurry at that point. All right, so quick recap for a converging lens. This is what makes things look bigger to help you with your farsighted if you cannot see up close and you need reading glasses, or a microscope makes things bigger, or a magnifying glass. They all work the same way. When it's far away from an object, we're going to see this in lab next week, it will make it upside down. When you're up close to it, it flips it back right side up and it makes it bigger, like a magnifying glass. And then if you're right at the focal point, it will have no image, the lines never meet, so it's blurry. All right, moving to the other kind. Most people your age, if you have eyesight issues, it's because you're nearsighted, which means you can see near but not far away. So you need glasses or contacts to help you see things that are far away. And what's happening if you're nearsighted is when the light comes into the lens of your eye, it bends it too much so that it meets in kind of the midpoint of your eye instead of back at the retina. So in this case, the light converges too early. Ooh, that should say early. And so what you need is when it converges too early, we want to spread it out a little bit more. So you need a lens that when it hits it, it opens it up a little bit and makes it converge later. The kind of lens that does this is a diverging lens. A diverging lens are going to be thicker on the edges. So if you are nearsighted and you wear glasses, if you take them off, what you're going to see is the edges around the glasses, around the frame are thicker. Sometimes they stand out over the frame, and the edges are thicker, and then it gets thinner in the middle. So I'm going to bring one to you now. This is a diverging lens, and what you're going to see is the edges are really thick and then it kind of caves inward on it. All right, when you put it in front of a paper, always, always, always notice that the actual object gets smaller and it stays upright. It never flips it upside down. So at any point along the way, a diverging lens makes something look upright and smaller. Very similar to a convex mirror, all right? So if you notice, the lenses and the mirrors do the same thing. You just have to remember which one goes with which. For this, then, as we draw the diagram, this is a different type of lens. So as we started off, it starts the same. I have my object over here, my principal axis, and then my diverging. These arrow tails are to show that it gets thicker on the edges and then thinner in the middle. You still draw a straight line into until you hit the surface of the lens. But then what happens to the light ray, when it hits, it opens up, it spreads open, it diverges, and it opens in line with the focal point on the left side. So you have to kind of think of it as going backwards. It goes through the focal point on the left side. The actual light ray goes like this. It opens up, we line it up with the focal point on the left side. The second light ray does the same thing it did before. You find the principal axis where it hits the lens. That midpoint right there is going to be where you draw your line through. And over here, they don't meet. We look to see the intersection point right there. And what you'll see is what you see in the lens. This is the image. It is shorter, it is smaller than the starting. It is pointing upright, it is above the principal axis, so it's upright. And this is what is going to be a virtual image. Anything that shows up on the left side is going to be virtual. If the intersection shows up on the right side, it would be real. If we take the object and we just move it closer, so now it's inside of the focal point, it doesn't change it, okay? So it'll still have the same idea. It'll go straight. It'll then open up through the focal point. It goes through and opens in line with the focal point. The second light ray still goes through the midpoint, and we will still have an intersection over here on the left side of the lens, right? It is still smaller than the original, it is still upright, and it is still virtual because it's on the left side. Okay, our equations for lenses, when we do the math, exactly the same for mirrors. You're going to have your 1 over f equals 1 over p plus 1 over q. You're going to have your magnification as hi over ho, which is also equal to negative q over p. Those two equations still work. The last piece is the sign conventions for lenses. When you do the math, f is going to be a positive for a converging lens, and then when you have to open it up with, think of anything on this side kind of as being negative, f, you have to put a negative sign in front of the focal point anytime you have a diverging lens. So when you do the math, if it's diverging and your focal point is 2, when you plug it in as 1 over 2, you have to do 1 over negative 2, just like with convex mirrors. So convex and diverging, you have to make the focal point negative. Okay, the height is still positive when it's upright, it's still negative when it's upside down or inverted. And then Q, it's mathematically going to come out positive when they show up. So the two arrows, when they show up on the same side, so both the intersection and the starting object are on the same side, that is when Q will come out negative, and that's when you have a virtual image. When, like on the front side, right here, our starting object and the image we see are on opposite sides, the lens is between them, that is when your Q is going to come out positive, when they're on opposite sides, and that is when you will have a real image for that. All right, that's what I have for lenses. Thank you very much.